Okay, let's get started. Meanwhile, other people will join. So, welcome you all to the live session 7 on the course manufacturing process technology, first and second. So, in this week, we are going to solve some of the practice problems based on the video lectures of week 7. So, let's get started. So, this is the first problem. Uh, you can give your response in the chat box. Please first try by yourself. After that, we will solve it together. Okay. May I audible to all of you? Anyone, can you please acknowledge whether I am audible to you? Hello, am I audible to you? Hello. Okay. Yes. If I am audible, uh, then please try first problem by yourself. After that, we will solve it together. I am waiting for your response in the chat box. After that, we will discuss it together. Any of you? Whether whether problem is clear to all of you or not? Are you finding any difficulty to understand the question? You can write in the chat box. Okay, am I audible now? Since no one is responding, that's why I don't know whether my voice is reaching to you or not. Hello, anyone of you, can you please unmute yourself and acknowledge me whether may I audible? Hello, may I audible? Can you please respond in the chat box? Okay. Yes. So, actually, I was waiting for your response. Okay. Yes. Okay. Now I will start discussing the answer of this problem. So, any of you have any doubt, please let me know after that. Okay. So, in this problem, what has been asked, the elastic deformations of a solid are observed. So, um what's the elastic deformation? So, if you remember, if we have a body, something like this, what will happen if we apply some load over it? Something like that. Let's say we are applying some load, let's say sigma. So, what will happen? So, then its dimensions will start changing. Okay, suppose it has some length L, and when we apply some load over it, then its dimension will change. But what will what will be happening inside the material? So during the elastic deformation, what happens? Let's start talking about the elastic deformation. Okay, suppose we have some body as something like this. Okay, and it is obviously it is made up of atom. Okay, so it is it is the condition when we are applying no load on the body. But what will happen if you apply some tensile load in the body? What will happen? There is some issue with the pen. Let me start it again. So when we apply some tensile load, what will be the situation? Tensile load. Okay, so suppose initially there was a gap of B between the atoms, but now when we apply some tensile load, let's say sigma like this, then there will be there will be a gap which is more than the B in between the atoms. What will happen when we apply some compressive load? Then what will happen? So if you see here, here now the gap is not same as the earlier one B. When we applied tensile load, then the gap has increased between the atoms. Yes, yes, Srinivas, you are correct. So now here we are discussing what will be happening inside the material. So earlier this is the initial state of the material, and this is the schematic representation of the when we applied some tensile load on the material. Then in case of tensile load we can see the there is a small disturbance between the distance between the atoms. Here if you see the B dash is little greater than the B, where B is the equilibrium distance between the atoms. Equilibrium distance between the atoms. But now if we see when we applied compressive load, now again let, let's say it's a B double dash, then what we observe, we can observe that B double dash is smaller than the B. So when we applied some tensile load, we can see mm, the atoms get stretched, whereas when we applied some compressive load, the distance between atoms gets reduced. And if we try to plot the stress strain curve for this process, how it will look like? So now I will add some another slide. Okay, now if we draw the stress strain curve for a typical material or metal, then how would it look like? So now I'm drawing some tensile engineering stress strain curve during the tension. Stress strain. How it will look like? Something like this. Okay. Mm. So there are several points. So this is the elastic limit. This point is called the elastic limit, and this point is called yield point. If you remember how we get the yield point, what we do, we will draw a parallel line to this. Okay, so if we draw a parallel line, but this has an offset of 0.2 percentage of strain value. Okay, so when we draw a line which is parallel to this is the elastic limit. Is what elastic limit here. This line remains straight till the elastic limit. After that, the transformation takes place and we get another set of curves. So this is the point that is called a yield point, and here we get the maximum value of stress during the tension, and that is called the ultimate tensile strength. And finally, this is called the failure point or fracture point. Or fracture point. So these are the some points which I have shown on the typical engineering strain curve. So till here, till the yield point, material goes under the elastic deformation. Elastic deformation. And after that, this complete region is plastic deformation. But but even in the plastic deformation, there are two zones. Here, this zone. What is this? Here also plastic deformation is happening, but here the deformation or the elongation is the uniform, or the cross section of the component remains uniform throughout its length. So here we call it uniform elongation. Uniform elongation. So up to the ultimate tensile strength or UTS, the plastic deformation which takes place inside a metallic material is uniform in nature. But what happens after that in this region? This is non-uniform elongation, or what we can say, suppose initially we has taken this specimen something like this, and we applied some load which is under the elastic range. So this is called the sigma y or sigma yield. So if the load value is less than sigma y, then our material will deform or elongate very small value, that is under the elastic zone. And what happens in the elastic zone, if we remove the load, then material will come back to its original position. And suppose if we remove the load, then the material length will again gets recovered if we apply load less than the elastic limit. But if we apply some load which is greater than the elastic limit or less than ultimate tensile strength, then again the length of material will gets changed. So here, suppose here we have length L0. Here in, if he here, second case, if sigma is less than sigma y. Third case is sigma is less than sigma UTS, but it's greater than sigma y. So here small delta L length will change take place, and it if we will remove the load, that length will get recovered. But in, if we apply the load which is greater than the sigma yield, then the length change will become permanent, something like this. So L plus, let's say delta L, but this, now this length is permanent, and the uniform in the cross section, if you see, it is uniform. But suppose if we apply more load, then what will happen? Then elongation will be permanent, but that will not be a uniform. It will look something like this, something like this. Here somewhere in between here, necking will take place. That is called necking. So it is the case when sigma is greater than sigma UTS. So this is the overall stress strain curve behavior, and now let's come to the answer of this problem. So elastic deformation of solid of observed 8. So here we see this is the elastic zone. All this region is the elastic zone here. So this, the elastic deformation occurs before the yield point. So the correct answer is the B. Okay. I hope it is clear to everyone. So still, if any of you have doubt, please ask me. Otherwise, we will move to the next problem. Is it clear to everyone? Please respond in the chat box. Okay, it seems it is clear to everyone. Now let's move to the problem number 2. Please try first. You can try it by yourself. Then we will discuss it together. You can give your response in the chat box. Okay. Okay, it is also an easier one. So what has been asked here? Metal forming is the result of gap of the workpiece. So what happens in the metal forming? What we try to achieve? The, if you see, the aim of metal forming is to change the shape of material without losing the material, or without melting the material. So what happens? Suppose we have some material like this, and what we are trying to do? We are trying to do change its shape permanently. So after the plastic deformation, its shape will become something like this. So what we did, we applied some load, we applied some load, issue with my pencil. Okay, Hamid, I got your response. Okay, I'm facing some difficulty with my pencil. Okay, but I need to close the app again. It's not here. Okay, we have added some load, and with the application of load, we try to change the shape of the workpiece, and that is called the metal forming. It is image shape change. Okay, and this shape change is permanent, and permanent deformation is what is called, it's called plastic deformation. So the correct answer is the A, the plastic deformation. I don't know why I'm struggling with my Apple pencil. So yes, so correct answer is the plastic deformation. Okay, so let's move to the next problem. Please try to give a response in the chat box. Which of the following metal forming process is best suitable for making wires? Okay, I am waiting for response from others. Okay, yes. So both of you are correct. So here I will try to show means uh, why it is a drawing process is really needed for the wires. So before that, let's quickly look at the all other processes. So again, we know all of these are nothing but metal forming process. Okay, so if you see a typical forging process, what we do, here, uh, it is just an example of one type of forging process, that is die forging process. Here we have the workpiece, and we are trying to change its shape by applying some load as well as some at some elevated temperature. So after forming, what we are doing, we are applying some load here, and we are bringing these two dies closer, and final shape of the workpiece will become something like this. Okay, so if you see the how the stress state of the system. So here the deformation is primarily being happening because of the compressive loads. Okay, so let's say this is sigma 1, this is sigma 2, and this is sigma 3. So this is sigma 2, this is sigma 3. So here all side compression loads are being applied in order to deform the material. So similarly, if we see the extrusion process, so this is an example of a forward extrusion process. So here what we had workpiece material, and we are trying to change the shape of material in some with uniform cross section. But here what we are doing, we are applying some, we are pushing the material inside. This is the die or the container, this is the container, and this is the die. Basically the final shape of the material will takes place with has the same shape as the die. So it may be circular, it may be tubular, uh, or it may be some eye section. It can be any complex section also, something like this. So this type of shape can also be extruded. So, but the thing is, the uniform cross section will always be remain constant. So for that, extrusion process is used. And now let's come to the drying operation. So it is here, if we see the uh, stress state in the extrusion, here also the deformation is mainly happening because of the all-sided compression loads. But if you see in the drawing process, here we had a billet or the rod. Now we want to change its cross sections to some desired shape. So earlier what we were doing, we were pushing in the case of the extrusion. But in the drawing process, what we will do, we are pulling the material from the here. So here we have die which is fixed, and here we are pulling the material, and this die is providing some reaction force, and because of this deformation is happening, or what we can see here, the reduction in cross section area is happening. So if we see the stress straight in the case of the wire drawing process, so in drawing process, a process is called the drawing process only if any one of the state is remain in the tension. So if we see, it may have compressive loads also, but uh, at least one load should be in tensile in nature. So that is called the drying process. So this is this drying process is typically it is used for the uh, making the wires or rod which have very simple cross section area, not very complex. So this is suitable for the wires. So uh, and another thing is that wire drawing process, it takes place at the cold, or let's say room temperature. So wire drawing process, it is done at the room temperature, or we can say it is a kind of cold forming process. And in the cold forming process, what we get good mechanical properties of the material. Well, in the case of the extrusion process, sometimes we need to elevate the temperature in order to uh, make the process uh, easier, or we should, so that we should need to apply less force. But extrusion process is not very faster process, it is a slower process. But wire drawing process is a faster process. and therefore we have to do it at the room temperature. If we want to manufacture the wire, then definitely uh, company will desire it to make it process as fast as we can. So in that case, uh, we need to deform the material at higher strain rates. So if you want to deform the material at higher strain rate, so in that case we don't want to compromise with the power consumption, as well as we don't want lose the properties of the final component. So since we know that extrusion process cannot be done at very high strain rates, only drying process is possible to do it high strain rate, and so that the production process will be faster. Therefore the best the best process which is suitable for the manufacturing the wire is, that is the wire drawing. So if you see the rolling process, you already have seen it many places. So here we are not able to manufacture the wire with having the circular cross section. So usually this is suitable for making plates, sheets, slabs. So those kind of things are suitable for the rolling, or uh, even the railway tracks which you see, that is also made by the universal rolling mill. So, but as far as the wire is concerned, we want faster process, and therefore the best process is the drawing process. So why drawing is the suitable? Because it is the faster, and we can do it at room temperature, and we don't want to apply much more load. Therefore we do it at the room temperature. So you can think of why we are doing it at the room temperature, why not at the elevated temperature. So if you talk about the flow stress, you might have seen that the sigma is equals to k epsilon to the power n. This equation you definitely have seen. This is called Holloman equation. So this is valid at the room temperature only. But suppose if we want to do deformation at the elevated temperature, at that time there is another equation which is also looks similar type, that is called, there is something like that, sigma is equal to c epsilon dot to the power m at elevated temperature. Here it is room temperature. So C is the strength constant, and M is the strain rate sensitivity. So M is strain rate sensitivity. So what we can see in extrusion process, I told that sometimes we need to increase the temperature of the material, and extrusion process cannot be done at the faster rate. And the wire drying process, we do it the room temperature, because we want to make the process faster. So here this equation is valid. Sigma is equal to k epsilon to the power n. But if we do it at elevated temperature, then you can see there is a term of epsilon dot, that is strain rate. So if we want to increase the process speed, it means we are increasing the strain rate. And if we increase the strain rate, then flow stress will become higher, or we have to apply higher loads. Therefore we don't want to do it at the elevated temperature. So therefore drying process is done at the room temperature, and is the faster process that is suitable for the wire drawing. So the correct answer is drawing process. So I have provided the answer of this problem, but still if any of you have doubt, please ask me, and if it is clear, you can write it in the chat box. shall I move to the next problem? If it is clear, please give your response in the chat box. Hello, may I audible? Okay, so okay, it means it is clear to everyone. So what I'm doing, I'm going to move to the next problem. Please read the problem and you can give your response in the chat box again. Yes, I have got response from the Sriniwas. I am waiting for others. So which of the following process is not a type of metal forming process? Others, can you please respond quickly? Okay. Okay. So, if you remember what what was our aim in the metal forming process? So, metal forming process, we were aiming for the shape change. Shape change. So already we have seen the process of extrusion, forging, drawing. Here we are doing the shape change. So why do you think injection molding is not the correct answer? Why injection molding? In injection molding, okay, let's start looking at the schematic of the injection molding. So it is a typical diagram of the injection molding. So what uh, what is being done here is that this is kind of we have cavity here, or let's say vacant space, and that has been created between the two portion of the, let's say, we call it die. And here we are charging the material charging the material in the molten state, and it is coming and it is going in the cavity. So here we had again what we did, we had material and we brought it into the molten state, and we had we have left it for the solidification, and finally we got the final products. And this, here we have the ejector pins. Basically we will remove this part and we will push the ejector pin so that the molded material will come out. So finally the material shape which we will get, it would look like something like this. Okay, something like this. So here also shape change has taken place, but still we are not considering the injection molding in the metal forming process. Can you think of reason why? Can you write in the chat box why it is not a metal forming process, whereas here also shape change is taking place? You can unmute yourself and you can tell, or you can write in the chat box why injection molding is not a metal forming process. Anyone? Okay, so let me help you out, but later on you can let me know if you have doubt. So yes, it is also here. Here also we are changing the shape. There are two things we are doing here. First thing is we are bringing them raw material to in the molten state, and then we are just pouring it inside the mold. So which is similar to the casting process. Here we are not applying any mechanical load to change the shape. Also here the here in the case of injection molding, uh, we get we will not get the final components which is required. We will always get some extra material, like here sprue resin will be there, like, so these are the some extra part which is not desirable. So these are things which are still there. So but in the metal forming, what we do, metal forming we do the shape change, but we are not losing any extra material, or we are not adding any extra material. uh, so whatever we had earlier, the the amount of metal or material is going to be the same after the forming process, and their shape change we achieve by applying loads. And even if you are increasing the temperature, but that should be less than the melting point of the material. So these are the few differences because of which we are not considering the injection molding as a metal forming process, whereas the here also shape change is happening. So, and injection molding is primarily, this term is used for, is applicable for the plastic materials. So if we take if we want to if we want some analogy in the metal, for the metals also, then probably die casting, this process is similar to the injection molding, but particularly if you talk about injection molding, this is applicable for the plastic materials. This term is used for. Okay, so I have explained the answer for this problem, but still, if any of you have doubt, please ask me. Otherwise, we will move to the next problem. Is it clear? Can you quickly respond in the chat box? If it is clear, then we can move to the next problem. Okay, since there is no doubt, then we will move to the next problem. Okay, thank you, Amit. Okay, please read the problem, and you can give your response in the chat box. Okay, I have got response from this Srinivas. I am waiting for others. Others, can you please respond in the chat box so that I could start explaining the answer? Okay, okay, let me help you out. So, what is the Tresca yield criterion? So, yield criterion is mainly uh, these are some criteria from which we come to know when any material or any component is going to deform plastically or yielding will start happening. So uh, these are there are the few criteria like von Mises, Truska, there are many more. So here in question it has been asked mainly about the Tresca criterion. So I will note it down what the Tresca criterion is. Sorry, yield criterion. This criterion you might also have studied in your solid mechanics course by the name of failure theories. So they are same. So basically Tresca criterion is used for as a failure theory in the solid mechanics, because there we are not interested in the plastic deformation. We always work inside the elastic zone for the solid mechanics, but here in the metal forming process we are mainly interested in the yielding of the material. So uh, since we are interested when material will yield, for that we need to know what are the conditions, uh, so that after which, after reaching that condition, the material will start deforming plastically. So if the statement of Tresca criterion is yielding will occur when largest shear stress, largest shear stress reaches a critical value. So so what happens? So suppose we have some component like this, and now what we are applying, what we are doing, we are applying some loads. Let's say some is compression, some is tension, or all maybe tension, or all maybe compression. So if you see here, we are just applying some normal compressive loads. Let's say sigma 1 and sigma 2. So what do you think? Here we are applying just normal loads, but Tresca criterion is talking about the shear stress. But we have applied only the normal loads. Do you think material will fail? So Tresca yield criteria is defined with respect to shear stress, but we are not applying any shear stress. We are just applying normal loads. So what do you think? Material is going to deform plastically or not? Yes, can you please, any of you can write in the chat box what do you think? Material will deform or not? Anyone? Okay. Okay, so yes, if we apply, if we reach some conditions, even by applying the normal loads, yes, we can deform the material, because it is not like the material has only this plane which I am showing here. So this is not like the material will can deform only in this plane. Even if you are applying the load, normal loads only, but there may be some other different planes will be there, something like that. In those planes, definitely, if we let's say if we are going to look this plane, then in this plane definitely some normal component of load will be there, sigma, and some shear stress will be there. Okay, so although the plane which I have shown earlier here in this plane, so xy plane, in this plane we are just applying normal loads, but apart from this plane there might be other planes also inside the material, where because of these normal loads, some component of this normal loads will come along this plane as a shear loads. If if these shear loads, so there are infinite planes are there, like these, like this, like that. So out of those infinite planes where there is a some shear component is coming, so out of those infinite planes the material will deform in that plane where this shear component will reach some critical value, or the tau component will reach some critical value. Then material will start deforming, although we haven't applied any normal load in xy plane. Okay, so this thing should be clear. So now let's talk about the how what the critical value is. What critical value should material has to reach in order to deform it plastically according to the Tresca yield criterion. So if you have you might have definitely come across the Mohr circle diagram. So how does diagram looks like? Something like this. So vertical axis is the shear stress, and horizontal axis is the, it is here we are showing the principal stresses. Okay, so principal stresses are nothing, these acts on the principal planes. If you don't know what principal planes or principal stresses are, you can go and revise, but I want to tell you briefly that principal planes are those planes in which only normal loads acts, or the we don't get any kind of shear stress on those planes. Only the component of stress which we will get on those planes, that are the normal loads, not the shear stresses. So the Mohr circle, in the Mohr circle, this I am showing it for the plane stress. Basically we have to, if you see in a plane in 2D case, we will get two principal stresses mutually perpendicular direction. So bigger one is sigma 1, smaller one is sigma 2, and from the sigma 1 and sigma 2 we can draw a circle with a diameter of sigma 1 minus sigma 2. So we can draw a circle with having the diameter of sigma 1 minus sigma 2, and this, or we can say radius of this circle, shows the maximum shear stress, tau max. So if this stress value or tau max value increases them if increases some critical value, then yielding will start happening. Now I have shown just for the 2D case. Now let's uh, what will happen for the 3D case. For 3D case, if we want to see how the Mohr circle looks like, it will look like something like this. Basically, in 3D case, we will get three principal stresses: sigma 1, sigma 2, sigma 3, something like this. And here we will get three sets of Mohr circle. Mohr circle is nothing, it is showing all the states of stresses which has been acting inside the material. So here we will get three Mohr circle, or what we can say, here we will get three sets of maximum shear stresses, or we can say this one is the, let's say this one is the shear stress or tau max 1. We can see this one as tau max 2, and we can see this one as tau max 3. Okay, so in the case of 3D case, we will get this kind of Mohr circle. Now what according to the Tresca yield criteria, if you talk about 2D, here tau max will become what? Tau max will become sigma 1 minus sigma 2 upon 2. Now if we see similarly in the 3D case, here we have sigma 1 is greater than sigma 2 is greater than sigma 3, and here we are getting three sets of tau max. So tau max 1, so tau max 1 is nothing, it's sigma 3 minus sigma 1 by 2, and tau max 2, if we see, it is nothing but sigma 3 minus sigma 2 by 2, and if you see the tau max 3, it is nothing but sigma 2 minus sigma 1 by 2. So if we see, this value is the highest one. So because if we see the difference, sigma 1 minus sigma 3, this is the biggest difference, and if this biggest difference, sigma 1 minus sigma 3 by 2, has crossed the critical value, then material will deform. If this is valid for the 3D case. So what that critical value is? So that critical value is nothing but it is the shear strength of the material in the uniaxial tension. So what is the criteria is? Criteria is that the sigma 1 minus sigma 3 should be some constant value. Okay, so this is general case. This is valid for all cases that we have derived from here. Okay, if I will try to show, so this is the 3D case and this is the general equation. So this value should be less than or greater than or equal to some critical value, then yielding is going to takes place. Okay, now how to find out what is this C value, what is the critical value? For that we will take a simple case, let's say for uniaxial test. So for the uniaxial test, what we have, we have material and we are applying just single load. or we are just applying the sigma 1, and other two, in that uniaxial case, sigma 2 and sigma 3 are 0. Sigma 2 is 0 and sigma 3 is 0. And when this material is going to deform plastically in the case of uniaxial tension, definitely it will deform only if the sigma value reaches the sigma yield, or let's say yield strength of the material. So now we will put the value here. Sigma 1 is there, sigma 3 is 0, minus 0 should be greater than or is equal to yield strength of the material. So what we can see? We can see the sigma 1 is equals to y. Now we come to know what should be the critical value. Critical value is nothing but y, which is the yield strength of the material in the uniaxial tension. So what we can substitute this value c. If we want to substitute the c, then we will get sigma 1 minus sigma 3. It should be greater than or equals to y, and that y we can, for any material, if you want to find out y, we will have to do tensile test, and from there we can easily find the y. So this is the all about the Tresca criteria. So shear stress, the maximum shear stress inside the material, if it reaches the yield strength of the material, then material will definitely deform plastically. That is the statement for the Tresca criteria. And which one is the correct answer then? A. Okay. So I have explained the answer of this question. If any of you have any doubt, please ask me, or I shall move to the next problem. Okay, it seems it's clear to everyone. So let's move to the next problem. Please read the problem and you can give your response in the chat box. Yes, I'm waiting. When waiting for response. Yes, I have got response from the Hamid. Others? Okay. So let's start discussing. So in a too high rolling process, what is the direction of the rolling of two rollers? So we know that in rolling process we are trying to deform the shape of the material with the help of sets of roller. So it may be two, it may be more than two. So based on that, there are different types of name given to the different configurations of the roller. So that I am showing here. So here this configuration is known as the two high rolling mill. So what is there? So basically, since two high is means we have two rollers. So this is the roller 1 or this is roller 2, and both are rotating in opposite direction in order to roll the, or this is the workpiece, and we want to roll this material, or we want to reduce the cross section area of the material. So both rollers are rotating in opposite direction. Here if you see, it is anti-clockwise, and here it is clockwise. So this configuration is called two high rolling mills, and this uh, because of this ro- rotating motion, the material it gets fed in between the gap of the two rollers, and it gets deformed in this region. Okay, so this is the configuration for the two high rolling mill, where one roller is rotating anti-clockwise and other is rotating in the clockwise. Similarly, we have three high rolling mills. So he, where if you see that this roller is rotating in anti-clockwise direction, and second roller is rotating in the clockwise direction, and again last roller is rotating in anti-clockwise direction. So what is happening here? The For the first time reduction, the billet goes in between the first and second rollers, and the deformed material again fed in between the second and third roller, and again it will get further deformed. So this type of configuration is called the three high rolling mills. Similarly, we have here the four high rolling mills, and sometimes we have basically these. If you see in the four high rolling mills, these two rollers are the rollers which are directly coming to the contact of the workpiece or the billet, and this is the responsible for the reduction in the cross sectional area, reduction in the thickness of the material, and these two are the backing rolls. So these two rollers are the backing the smaller rollers, and smaller rollers are used so that we could give more um, we can give more deformation, more localized deformation to the workpiece. And similarly, for uh, difficult to roll material, again more sets of roller is used, that is called the cluster mills, and sometimes tandem rolling mill is also used, where a reduction in cross section area, or reduction in thickness of the billet takes place in step by step process, so we don't have to feed the material back and forth. Here the material is moving in the same direction, and step by step its cross sectional area is being reduced in order to get the final sheet. So these are the few configurations, but if you talk about the problem, here it has been asked only for the two high rolling mills, and the correct answer is uh, clockwise and anti-clockwise, this D1. So any of you have any doubt in this problem? So shall I move to the next problem? Okay. Okay, so let's move to the next problem. Please, you can give your response in the chat box. After that, we will discuss it together. Okay. I have got response from the Hamid. What are the things. I'm waiting for others. So I'm waiting for others. Please, can you others please respond in the chat box? Okay. Okay. So let me start discussing. So, which of the following is not a type of extrusion process? So, if you could remember what we were trying to achieve in the extrusion process is nothing. It is also a metal forming process. Metal forming process. Here, by this process, we can get a component which has uniform cross section. Cross section. So let's start looking what kind of extrusion process uh, usually exist, which are the most common of the extrusion process. So first one is the direct extrusion process. So in direct extrusion process, what we have we take some billet material or workpiece material. We take billet material. We we push it with the help of the ram, and in the front we had a die with required cross section. It may be tubular, it may be square cross section, it may be I section, it may be any complex section. So die has the shape of the required cross section. So we push the material from the back side, and the material flows, and it takes the shape of the uh, die. So it so extrusion process can uh, it it can be done at the elevated temperatures, or it can be done at the room temperature based on the properties of the material and the required product. So this is the configuration of the direct extrusion process. So let's try to see what is the next configuration of the extrusion process, that is the indirect extrusion process. So indirect extrusion process, what happens indirect, if you see in the direct extrusion process, we are giving the velocity to the ram in this direction towards the left, and final metal is also coming out, the final product is also coming out towards the, it also has that velocity towards the left. So but if we see in the indirect extrusion process, what we do, we take the billet or the raw material, and we had a ram, we had shape of ram, something like this. Basically this ram itself contains the die at the end. So this portion is the die which has the required cross sectional shape, and here we apply load and we give some velocity, let's say we are here, but now our die is moving towards this word, towards the right side, but the material is confined inside the container. This is the container, so it is confined inside the container. The only opening it is there, that is here in between the gaps of the die, and therefore the material flows from, let's say, here to here, something like this. So material is coming here, so it is So we are giving velocity to the RAM to the right side, but the product is coming out towards the right side, toward the left side. So this is also a extrusion process. Basically, we are applying compressive load to the material, and material is coming out from the gaps between the die. But now its direction is in reverse direction of the movement of the ram direction. Whereas the earlier case in direct extrusion, the ram direction was same as uh, the velocity of the direction of the product. So this is the indirect extrusion process. There is one more that is called the hydrostatic extrusion process. So it is more or less similar to the forward extrusion only, but here if you see the contact surface, if you see the contact surface from the ram to the billet, basically we are directly applying the load on the back side of the billet with the help of ram. So what is drawback here? The drawback in this case is, suppose we are applying some sigma load here, but in the reaction from other side, the loads will not be the same as the sigma. It may be different. So it may be, let's say, some sigma 1, or from here side if you see it's here sigma 2. So the loads which are applying on the billet, it is not thus equal from the all sides. So in order to achieve the uh, uniform load from the all sides, what we do, we apply some liquid or some fluid in between the billet and the ram. Now we are not pushing the billet, now we are pushing the liquid, and we know that the liquid has properties that it distributes the pressure equal in all directions. So because of that, now the billet will experience equal amount of force or stress from the fluid, and its material will flow towards the outside. So we are able to achieve the equal amount of stresses from the all directions only because of the fluid, and that is called the hydrostatic extrusion process. So let's start looking at the options of the problem. So which of the following is not a type of extrusion process? Yes, direct extrusion is there, indirect extrusion is also there. So stepping extrusion, it is this is the not any kind of extrusion process. So the correct answer for this question will be the C. So yes, C is the correct answer. Still, if any of you have doubt, please let me know, or we shall move to the next problem. Okay, since there is no doubt, so we will quickly move to the next problem. Please read the problem and first try to solve it by yourself. After that, we will solve it together. So please take some time to solve it by yourself. Whether problem is clear or any of you have any doubt, please let me know. If you are facing difficulty to understand the problem, please let me know. And if it's clear to you, then you can solve it. You can give your response in the chat box. Are you able to solve it, or I shall start discussing it? Can any of you please respond in the chat box? Or you need some more time in order to solve it? Okay, so let me help you out. So, what is given in the problem? So, the strength coefficient is equal to 550 MPa and strain hardening exponent is 0.22 for certain metal. During the forming operation, the final true strain that material experiences is 0.85. And what we need to find out, determine the flow stress at this strain and the average flow stress at the metal, average flow stress that the metal experienced during the operation. So uh, if we talk about the stress strain curve again, this is the stress, this is the strain. So we will talk about the true stress strain, okay? Sigma and epsilon. So how it looks like? So it looks like something like this, okay, for a typical material. So till here we have elastic deformation, and after that this is the plastic deformation. And if you remember, then of in this region the equation of curve is linear. So in this region, if we see what is the equation of curve, this is the sigma is equals to Young modulus times epsilon, something like that. And if we see what what is the governing equation of the plastic region, that is nothing but sigma is equals to k epsilon to the power n. So this is called the Holloman hardening law. Holloman hardening law. So what is sigma here? Sigma here is the flow stress of the material. Stress of material. Epsilon is the true strain at any particular deformation. So here, let's say here is the strain of epsilon. Just epsilon is nothing but the true strain. So at this true strain, let's say epsilon, how much flow stress will be there, that we can calculate from this equation. And what is the K? K is the strength coefficient. And N is nothing but strain hardening exponent. So now let's see what is given in the equation. So we have given the strength coefficient 550 MPa. It means K we have given. And what else is given? Strain hardening exponent N is given. And what else we have given? Strain at which we need to calculate the flow stress, that is also given. Now we just need to substitute the value in order to calculate the flow stress, that is the sigma is equals to K epsilon to the power n. If we substitute the value, we will get that will comes out 530.68 MPa. Okay, so that is the flow stress that we need to find out. So we have find out the flow stress at the given strain, and what else we need to find out, that is the average flow stress. So what is the average flow stress? So average flow stress, it can be much more clearly understand in terms of area under the stress strain curve. So suppose we have stress strain, true stress strain curve, something like this: sigma true and epsilon true. So it has some area. Let's say here we have this epsilon. For given strain, we have plotted the stress strain of a material, stress strain curve for a material, and it looks something like this. But if you want to draw an equivalent perfectly plastic stress strain curve, so how we will do that? Basically, what we want to represent the same properties of the material, same properties of deformation of the material by some perfectly plastic uh, properties of the material. Or suppose if we have perfectly plastic material, then how it will look like for the given strain value. So in that case, this is the typically how the stress strain curve for the perfectly plastic material looks like. So what we can say, this is, let's say, sigma average. This is the average value of stress to achieve the similar strain value which was here. Okay, so how we will show the equivalence, or how we can show them the equivalence between them. So the only thing which we have, that is the area. So suppose if the area of these two curves are the same, then some kind of equivalence we can say there is some equivalent representation of the same material for the perfectly plastic nature. So for that, if you want to equate the area, what we will get, we need to calculate the area of these two curves and we need to equate them. And what the area gives, it gives the work per unit volume of the material. Okay, so area under stress strain curve gives the work which required to involve which requires to be to in order to deform the material up to the strain value of epsilon. So we are equating the work for these two materials. One is the real actual material and another is the perfectly plastic material. So we are comparing the work for in order to deform the material up to the strain of epsilon. So we want to find out what is the average stress value which we have to give to the perfectly plastic material in order to reach the strain value of epsilon. So now we will calculate the work for the our actual material, that is that sigma into d epsilon, and from where we have to integrate 0 to epsilon. And what else we know, sigma is equals to nothing but k epsilon to the power n. And if we substitute it here, what we will get, work will equals to 0 to epsilon, k is the constant, epsilon to the power n times d epsilon, and if we integrate it, what we will get, k epsilon to the power n plus 1 divided by n plus 1. This is the work which we have calculated for our material, for actual one. And if we calculate the work which is required for perfectly plastic material, what we have, if you want to calculate the area under this curve, this is nothing but sigma average times epsilon. So this must be equals to, so work here is the sigma average times epsilon. Now we are equating the both work times epsilon. So if epsilon will, if we will get the epsilon common from both sides, that is epsilon to the power n times epsilon divided by n plus 1, that is equals to sigma average times epsilon. This will go away, and what we will get, the equation for the sigma average, k epsilon to the power n divided by n plus 1. So this is the formula we will get for the average stress value. And now we need to substitute the values which already we have, that sigma average equals to k we know, that is a 550, and epsilon we know that strain is 0.85 and n is the 0.22 divided by n is 0.22 plus 1, and if we calculate it, we will get 434.9 MPa. So the sigma average value we have got approximately 435 megapascals, and flow stress value which we have got, that is here, that is near about 531 megapascal. So the correct answer for this problem is B. Okay, so is it clear to everyone, or any of you have any doubt? Anyone? It's clear. Can you please respond in the chat box? Yes, sir. Once keep the next slide. Okay, here. Please look at it. This. Okay. Hamid, now it's clear, or I need to explain again somewhere? Okay. Okay. So I moving to the last problem of the day. Okay. So please read the problem, and you can give your response in the chat box, and after that we will discuss it together. And if you are finding any difficulty to understand the problem, please let me know. Whether problem is clear to everyone, or I need to explain the problem. Do you understand what is the meaning of the draft in the rolling process? Okay, let me draw the diagram of the rolling process, then probably you can understand easily. So, so what we do in the rolling process, we have some plate, or we have some slab, or we have some billet. What we try to do, we try to reduce the thickness of thickness in the rolling process. So suppose we have initial thickness, let's say capital H, and after the rolling, oh, so our rolls are rotating something like this, then only it will the then only billet will get fitted inside in between the two rollers. So initially we has a thickness of, let's say this is the, I would draw in 3D. So something like this. So initially we had height of the, or the thickness of the slab, let's say H, and after rolling process it has become, let's say, small h. Now what is the draft? Draft is nothing but reduction in thickness h minus h. So that is the draft. And here in this diagram, if you see this diagram, here only half portion of the this diagram is been shown. So if you see this diagram, so if you cut it from the half, then half portion of this diagram has been shown there. So what we can say, this delta h is nothing, it is a draft, that is h minus h. Since delta here in this diagram it has been shown only for the half portion, therefore the reduction, if you see that this is the reduction in the thickness in the half portion of the billet. So this is the half portion, that's why it has been written as delta h by 2. So basically what has been shown here, it is the half of the draft. So what we need to find out, we have to find out the maximum value, maximum possible value of the draft for the given roller. So roller has a radius r, and for the roller radius r, what is the maximum possible value of draft which we can give, or what is the maximum reduction in thickness can be possible in the one pass? That's what we need to find out. We need to find out delta h max. Okay, so up to here it is clear to everyone. So what has been asked in the problem, that's what I have explained till now. So is it clear? Please respond in the chat box. If it is clear up till here, then only I will move to the next. Anyone? Can you please quickly write in the chat box if it is clear to you, or I need to explain it again? Am I audible? Anyone? Can any? Okay. Okay. Shall I move to the next? Shall I move to the towards the solution of this problem, or you want to try it by yourself? Okay. So let me start explaining the solution of this problem. So basically we want to calculate delta h max, which is the draft. We are doing the rolling process in order to reduce the thickness. So definitely we will be looking for, if we have, suppose we have a rolling machine which has fixed diameter of the roller, definitely we will be interested in what is the maximum possible value of reduction in thickness which we can achieve in one go. So that we need to find out. So that's what I am going to uh, that's what I am going to find out. Okay, so now I will clear this diagram a little bit. Okay. Okay, so here we had a roller of radius r, correct? And if we see if we see at the point of contact of the billet from the roller, then there will be two types of forces must be acting on the billet as well as the roller also. So if we see the forces which are acting on the billet, that is the normal force or Fn, and another force which is acting along the perpendicular direction of the normal, that is the frictional force. So there is a friction between the surface of the roller and the billet, and because of that the force of friction is acting towards the uh, towards the tangential direction of the contact. Okay, and right now some angle alpha is being made over here. Okay, so what do you think, when the rolling process is possible, how the rolling process will happen? Basically, in order to rolling process to happen, our billet, which is this, it should go inside the in between the rolls. Okay, suppose there is another roller here, which is it is rotating this side, it is rotating this side. So this billet should get pulled inside the roller. So, so if you see the force diagram, according to force diagram, if we see the normal force, and if we see the normal force, and if we try to resolve it into two directions, one is here, one is there. Okay, so this is the Fn, and that is the horizontal component, and that is the Fn, that is the vertical component of the normal force. And same time, if we try to resolve the frictional force, friction force is here, it also has two components. One is towards the downward, that is the downward force, that is if we call it Ff vertical, and another component is along the horizontal direction, that we call, let's say, Ff horizontal component. Okay, so if you just focus on this point, what we can see, we can see two forces are acting. One is towards left, one is towards right, one is towards left. Okay, so this one, the right word, is because of the normal component, that is F and H, and the left word is because of the frictional component, that is F F H. So rolling process will only happen if our billet will come in between the two rolls. That means this horizontal component has to be the greater than this horizontal component, or the rolling process will possible only if the horizontal component of this frictional force is greater than horizontal component of the normal force. Otherwise our billet will not come inside the in between the two rolls. So is it clear up to here? Hello, can you please quickly respond in the chat box? If it's clear up to here, then we will move to the next part of the solution. Shall I keep on explaining ahead? Okay. Okay. Now, one thing we have understood, The rolling process is possible only if the horizontal component of frictional force is higher than the horizontal component of the normal force. So if we want to write it in the terms of equation, so what we can write for rolling to happen, then ff cos alpha should be greater than or equals to fn sin alpha. So what I was telling in the sentence, that's what I have written here. Okay, and there's another relation which is uh, which is there between the friction and the normal. We know friction force is nothing but mu times of normal force, whereas the mu is the coefficient of friction between rollers and billet. Okay, so if we want to if you want to know what is the maximum reduction which is possible, in that case this inequality, this thing will become equal, or the maximum height which is possible, maximum reduction which is possible, that will come, that condition will come only if this frictional horizontal component of frictional force will be equals to horizontal component of normal force. Okay, and if we use these two equations, what we will get? We will get ff by fn is equals to sin alpha by cos alpha. Okay, and from this, what is this? This is nothing but this is mu, or we can say mu is equals to sin alpha by cos alpha is nothing but tan alpha. Okay, this relationship which we have got till here. So for a rolling process to happen, we need to we have find out the relationship between the tan alpha and the mu. Mu is equals to tan alpha. And now what we are looking for, we are looking for h max. So we need to bring h max somehow for this relationship mu is equals to tan alpha. Okay, so let's try to look closely at the geometry. So it's something like this. Our billet is coming here and it is exiting here, and what we know that this gap, this is nothing but delta h by 2, and let's say this is the center, and from the center, if we connect this line, this is nothing but radius, and if we drop a perpendicular here, what is this length? This is nothing but r minus delta h by 2. Now this is right angle triangle, and this is nothing but alpha. Okay, and till now what we have got the relation is equal to mu is equals to tan alpha. Okay, so tan alpha is nothing but sin alpha by cos alpha. And let's say I am giving some name this to triangle OAB. So in triangle OAB, what is the cos alpha? Cos alpha is nothing but this base upon hypotenuse, or OA by OB, that is equals to R minus delta H by 2 divided by R. And if you simplify it, we will get 1 minus delta H by 2R. Okay, so cos alpha we have got this much. Similarly, if you try to find out what is the sin alpha is nothing but it is from the identity, it is 1 minus root over 1 minus cos square alpha. Okay, now we already know what is the cos alpha. We will substitute this here. So what we will get, 1 minus, now this is the value of cos alpha, and what I am doing, I am substituting the value of cos alpha whole square. Okay, and if you solve it, what we will get, 1 minus 1 plus delta H by 2R minus delta H by 2R to the whole square. Okay, and one uh, one assumption which we have to take, basically this is true, that if you see the roller, it is much greater than the reduction which we are getting. Basically, if you see the radius of the roller, it has, let's say, radius more than 100 centimeter, but if you see the delta H value, it is very small, let's say 5 mm or 2 mm, something like that. So delta R is very greater than delta H. So if you see this equation, if you uh, this will approximate to the 0, because if we take the delta H, if we take the square of the delta H, this will become even smaller. So we will neglect this term, or what we can say, we will get sin alpha is equals to, approximately is equals to, 1 will go away, we will left only with delta H by 2R. So now we have sin alpha, we have cos alpha, and we have a relationship of mu and tan alpha. So now what I am going to do, I am going to put the value of sin alpha and cos alpha in this relation. Mu is equals to tan alpha. So mu is equals to, I am putting the value of sin alpha, delta H by 2R divided by cos alpha. So cos alpha is nothing but the 1 minus delta H by 2R, should be square of this whole thing. Okay, or what I can say, it is something like this, delta H by R divided by 1 minus delta H by R plus delta H by 2R to the whole square. And again we will, since here delta H square term is coming, again it will go to 0, and we will left with root over delta H by R minus delta H. And if you further simplify it, what we will get, root over delta H over R. So basically here what we are doing, R is much greater than delta H. So if we subtract a very small thing from R, delta H, we will again get R. So that's why we have substituted this with the R. So final relationship which we have got is something like this: mu is equals to root over delta H by R, and this relationship we have got by considering the extreme condition where the rolling is possible. It means if we find out delta H by this relationship, that will be the maximum possible delta H, or that will be the maximum possible draft. We cannot get the more draft from this. If we try to give the more reduction more than this delta H, definitely our billet will not get feeded into the roll with the given value of friction value. So uh, again, if we square it from the both side, what we will get? Delta H is equals to nothing but mu square R. So that is the final, or let's say delta H max we will get. Okay, so the correct answer for this problem is the first one. So I have explained the solution of this problem. So is this clear to everyone, or if there is doubt at some step? Okay. Okay, others, is it clear? Any one of you, any doubt? Problem 7. Problem 7, this one. Yes, Nishu, please tell. So, if I will quickly try to explain, uh, so basically here it has been asked which of the following is a not type of extrusion process. So first of all, I have explained what kind of extrusion process which are there. First one is the direct extrusion process. Here we are pushing the billet with the help of a ram, and our product is also coming out in the same direction. Here we are giving the velocity to the ram towards the left, and product is also coming towards the left. That is called the direct extrusion. Whereas in the next case, uh, here we are giving the velocity to the ram towards the right side, but the product which is coming out, it is towards the left direction. So here the velocity of the ram and the velocity of the product is opposite. Therefore, it is the indirect extrusion process. So it is happening because of the geometry of the uh, die and container set which we have taken. Here we are squeezing the material. Here we are squeezing the billet is here, squeezing the billet here. Oh, sorry, I will take it. Here, this is the billet we have, and we are squeezing it with the help of the die, and only opening is there in between this die. Here only we have opening. So only, therefore the material is flowing like this, because only direction which is open for the material movement is this, towards near this, and therefore we are pushing the material towards the right side, but the billet is coming towards the left side because we have left the gap so that material could come only towards the left side. So that is the indirect extrusion process. And last one is the hydrostatic extrusion process. Here we are not direct. Here the here we have billet. In earlier cases, if you see, we have billet. We were pushing the billet directly with the ram, but in this case we are not pushing the billet with the ram, whereas there is a fluid, there is a layer of fluid in between the billet and the ram, and we are pushing the liquid, and this liquid is applying the hydrostatic load to the billet. Basically, this liquid is squeezing the billet material, and because of this compressive load, billet is moving outside. A is extrusion. Hamid has some doubt. So this is the hydrodynamic extrusion process, but we are not aware of any kind of extrusion process which is known as the stepping extrusion process. That's why this is not a type of extrusion process, whereas the direct extrusion, indirect extrusion are the type of extrusion process. Therefore, the correct answer was the C. So, Nishu, still there is doubt or some more explanation is needed in this problem. After that, I will come to the Hamid's doubt. Okay, now it's clear to the Nishu. Hamid, A extrusion, B forging, C drawing, D shearing. Answer is shearing, right, sir? This is for which problem, Hamid? I am not aware of this question which I have explained. Hamid, you have written some doubts, but it is recording to with question. So this is the option you have given. So what was the okay? Which of the following is not a bulk deformation process? Extrusion, forging, drawing, shearing. Okay. So what I can do, I can give you a hint, and from that you can able to solve it by yourself. So so if if you know what kind of forming process we have studied, let me add another slide, then probably it will be easier to insert new slide. Okay, so how many types of metal forming we have studied? Metal forming process, there are two types. One is the sheet metal forming, and another one is the bulk metal forming. So here the only difference is that if you talk about the bulk metal forming, so in this case, sorry, in the case of bulk metal forming, we can deform the material from the all sides, and there is no restrictions in any particular direction. So here we can deform the materials from the, let's say, in the along the x-axis, or let's say the y-axis, or let's say the z-axis. From all sides we can deform the material, but in the sheet metal forming, we have one dimension which is very smaller than the other two dimensions. Let's say sheet. If we have sheet, definitely it has some width, it has some length, and it has some thickness. So here, if you see, thickness is much smaller than either length or width. Okay, so here, if you want to change the shape of the sheet, definitely we are not interested in reducing the thickness of the sheet. We want to fold the sheet something like this, or we want to give some don't we want to change the shape of the sheet without changing its thickness. Okay, so here we are not interested to change the thickness of the sheet. We are interested only to change the shape of the material. Like from the sheet, what we can do, we can make a cup, something like this. Okay, by the deep drawing. Or from the sheet, we want to bend it, something like this. And if you talk about, if you want to cut this sheet, what we have to do, we have to shear it off. So basically, suppose we have sheet something like this. So I will draw another. We have sheet here, and if we want to cut it into two parts, how we will cut it, we will shear it off. So basically what we will do, uh, we will try to shear the material. Basically we have press, or we have, with the press we apply the shearing load like scissors. How you cut the papers, you have two jaws, and with the help of two jaw you are trying to cut the paper. Basically what you are doing here, you are trying to shear the paper. Here also, if you want to cut this sheet into two parts, we are trying to shear it off. We have applied some shear load, and because of which these two metals gets cut into two different pieces. So shearing is, this operation is for the sheet metal process. And whereas if we talk about the other process like extrusion, what we are trying to, we try to deform the bulk material. So basically if we have big big cylinder, we want to make rod out of it. What we do, we will put it inside the extrusion die and we will push it by the ram, and finally we will get a rod with smaller sections. Here we have deformed the material from the all sides. Its length has changed. Its, if you see it, it has been deformed in the x direction as well as in the y direction as well as in the z direction. So this is the bulk deformation process. Similarly, forging is also a bulk deformation process where uh, we have some component like this, we and we applied some forging load, then the shape of material has been deformed in all three directions. So it has become elongated here, its dimension has increased here, but its thickness has been reduced. So forging is also bulk process, extrusion is also bulk deformation process, and drawing, like I have told, the wire drawing, or sometimes we do the tube drawing. So wire drawing, what we will do, suppose we have billet of something like this, and we are trying to reduce its diameter, we are trying to increase it in length, something like this. From this cylinder we want to make a wire. What we have done, we have increased its length, we have deformed it in all direction, the x, y and z directions. So this is also a bulk deformation process. So apart from the shearing, other all processes are the bulk deformation, and whereas the shearing is the metal uh, sheet metal forming process. So this is not a bulk forming process, this is the sheet metal forming process. Now it is clear. Okay, okay, any of you, any more doubt? Okay, if there is no doubt, then we can end the session here, and we will meet at the next Tuesday with some problem based on the lectures of the week 8. So good night all, and we will meet at the same time next Tuesday. Okay, bye, good night everyone.